Earlier, we analyzed the motion of a soccer ball that looked like it was moving in the same direction at the same speed. And we also constructed a computer model to predict the motion of the ball. And by eye, the predictions seemed reasonable. Today, we want to look at the observations and predictions together more carefully. In the overall scheme of our thinking, today's discussion will link the earlier observations with the construction of the modeling by engaging in the process of evaluation, where we will compare our observations to our model predictions and constructively critique the comparison. To do this, we're going to focus today on comparing the ball's observed position and the predicted position plotted versus time on the same graph. We'll discuss here the first steps for making this graph in a spreadsheet. To obtain the predicted position versus time for the model, we need to activate certain lines of code in 3 separate places marked by the word optional in all caps. We can make the code lines we need active by uncommenting those lines. That is, by following the instructions that are given in each section and uncommenting by removing the leading hashtag symbol so that you end up with a code that looks like this. Our code file lives in some directory on our computer. When we run the code, it will generate a new file named pythontest.csv in that same directory. This file can be opened up in a spreadsheet. The way we have our code set up now, it will write the time and the x position of the ball into that file once every iteration. We can modify this line to write out whatever quantities we like. Just note that every time we run the program, the CSV file will be erased and written over. Now, to obtain the observed position versus time, we open the tracker file as shown here, containing the position data we determined from our earlier analysis. We can cut and paste the corresponding x position, observed x position, and corresponding time into the same spreadsheet that contains our predicted positions. Now, given the wide variety of possible spreadsheet applications that could be used for plotting, we will not go into details about that here and handle that discussion about spreadsheets elsewhere. Instead, what we will do is we'll go directly to the plot, the graph, showing the comparison between the observations and predictions, where the observed positions at different times are shown in blue squares, and the predicted positions are shown by a black line. First, we should recognize that at early times, the predicted positions aren't really predictions. Recall, we used our observations to set the initial conditions for our model. We used the first observed position and corresponding time to set those quantities in the model, and we used the first and second observed positions and corresponding times to estimate the initial velocity of our ball for our model. We always need to do something like this. We always need to start out with this information to predict the motion future using Newton's second law, because that's what Newton's second law says. To predict a new velocity, Newton's second law tells us that we have to begin with an initial velocity, and then with that new velocity, we need also to have a position, an initial position or location where the object is to begin with. The initial position and velocity are crucially important because they contain all of the history of the ball we need to know, all the way back to the beginning of time, in order to begin making predictions of the translational motion future of the ball. The rest of the predicted motion, plotted in black, is really a prediction. It's good to talk through how the computer model works to make that point. Before we do that, let's remember that the model implements our fundamental principle here, Newton's second law, where beginning from initial conditions and knowing the system mass, we can look a short time into the future, and we can predict the new velocity as well as the new position. But to make that all work, we need to specify the total interactions, which in this case, we make the assumption that they are 0. This is exactly what the code is doing. Starting from the very beginning with the initial position and velocity we just discussed, and under the assumption of no net interactions from the surroundings, apply Newton's second law to predict the new velocity a short time later, then use that to predict a new position, and now at the new time, small time interval, delta t later, we start over and we do the whole thing again and again and again. With each pass through the loop, we keep advancing the time a small time step delta t. So the predicted position versus time shows, as we saw in the graph, a linear behavior. But that line isn't predicted all at once, but rather is the outcome of an accumulation of predictions, each of which is made one small time step, delta t, at a time. The end result, starting from 0 net interaction as our assumption, looks like it does a good job of predicting our observations. But it's good to make some critiques to make improvements. Let's apply our evaluation process on the experimental side, where if we look at a little more closely the motion of the soccer ball, we would notice that the ball not only goes from right to left, but also drifts a bit from front to back. So, perhaps, if we look at late times, maybe this could explain why we overpredict a little the observed position of the ball. We can also apply this evaluation process on the developing explanation side, in this case to refine our understanding. Looking at our computer model, we notice that a change in the velocity, the second term on the right-hand side of Newton's second law, is always 0 because F net is 0. So we see that, in fact, the object's mass, in this particular case, plays no role in the prediction. Moreover, because this leads to constant velocity, then our position predictions would still be good in this particular case, regardless of how large delta t is. This means we could write a simplified model of the motion with the beginning time at t equals 0 in just this way, where we recognize the function x of t as the equation of a line with slope v naught, the x component of velocity. Now, it's tempting to ask, why didn't we just start with these equations and save what seems to be a lot of bother? Well, this specialized set of equations helps us here for a particular case of constant velocity, but if we encounter some other situations, which we will soon, where we see the object moving, perhaps with changing speeds or directions or both, these equations won't cut it as a starting point. So, to prepare ourselves to handle a wide variety of real-world motion cases, we need to start with some powerful voodoo, something that we're confident will always work. So that's why we'll start with fundamental principles. Some final points. Newton's second law for no net interactions has a special name. It's called Newton's first law. Here's one way to state Newton's first law. When our system has no net interactions with its surroundings, the system moves at constant velocity. Now notice, no net interactions does not necessarily mean no interactions. So, for example, if we look at the soccer ball we saw earlier, we're pretty confident that the soccer ball is interacting. It has the pull of the Earth's gravity, and the ball is in contact with the surface.
Newton's first and second laws don't let us figure out how many interactions there are in any given situation. All they tell us is that if the interactions add up to 0, The object must move at a constant velocity. Later, we'll see that all we need to know to predict the translational motion of an object is the total force on that object. That's all that matters to Newton's second law.
Now for the zero net force case, you might have thought that no net force means the object doesn't move. It remains at rest. Well, that is one way for the system to have a constant velocity, a constant zero vector. But we now know, and we have seen, that we can also have a velocity that is non-zero and constant, meaning we have motion in the same direction at the same speed. Incidentally, our code could handle this case, predict the case where the ball moves, if you want to call it that, with zero velocity. How can we modify our code to do that? Here's the answer. We see here that we would have to have, at the start of the motion prediction, the object's initial velocity be equal to the zero vector. How did it get that way? Our model doesn't address this. As we said before, the initial conditions describe the past history we need to know when we start to make predictions. But the initial conditions don't tell us why the initial motion started the way it did.